So this lecture I call the detailed facade. It's really an examination of the punch facade, the idea of an opening in a wall system. It helps us to focus on the idea of reducing glazing area for increasing the performance of a wall by creating less glazed area and more highly insulated areas. And that comes along when we talk about rain screens into a bit of complicated detailing in order to create both nice aesthetic facades and high performing facades. So I thought it would be good to kind of conclude our examination of facades, kind of looking at those kind of details. Before we do that, though, I want to talk a little bit about rain screens because I found some nice resources, kind of pushing it back towards the residential area, which will be something I think um, will be more significant in the future coming along. So I'm going to click out to the PowerPoint presentation. This is by the Rainscreen Association of North America. I'll go through these really quickly because we've really learned most of this, but what kind of got my interest was that it was focused, this presentation specifically on residential applications. And we have obviously the presentation of the typical wall assembly with the ideas of moisture migration, kinetic and rain-driven moisture, and all the issues that go along with it. An interesting study by the EPA about significant amounts of water damage in 85% of 100 buildings examined, and 90% of those failures are in wall systems. And as I've shown you before, these kind of failures, especially around window systems and other penetrations in the wall, can really wreak havoc with the internal structure, creating mold. In this case, it was nail penetrations in this one case study. Another place it was just the deterioration of the sill detail, all hidden under the siding system, unavailable to be inspected, and for sure unavailable to dry out and perform as it needed to. So it talks about how expensive they are, how little insurance it can recover that cost. Once again, this kind of oriented towards, I guess, inspiring contractors to look at this idea of moisture management in a more significant way. A good example of relatively new construction, as it says, but the growth of mold within the wall cavity because of moisture and condensation. An interesting chart about how quickly mold can form and then start to grow. Once again, back to that idea of builder liability. These are a couple of charts kind of indicating how significant, especially for us, these ideas of these problems generated by water, moisture, and in our case, snowfall also. This is unrelated to the rain screen one, but this is a great chart showing you this kind of idea of intensity and design intensity for wind speeds. So we're looking at off the coast of Miami at 180 miles an hour. We go up the northeast seaboard. We can see wind speeds of 150 to 140 miles an hour. And those are, I guess, as we dealt with in facade deflections, those are the kind of forces along any work that you might do on coastal locations, or even actually quite inbound of coastal locations, but still near the coast. And obviously not on the radar map of us in Western New York, but as a practicing architecture student or practicing architecture architect of the future, you should be aware of this idea about the significant requirements of wind-driven issues, and that can include moisture when we talk about rain screens. Turns out that for us, though, in the Northeast, that we live in a dense area with a lot of moisture problems. So we're looking at this kind of density map, overlaying with the probabilities of moisture, humid, rain-driven, snow-driven kinds of water intrusion. And then, like I said, I want to go through this relatively quickly. You talk about the mechanisms. We talked about them: capillary movement, things too close together or very close together allow water to be sucked in, kinetic energy from that wind-driven load. I want to spend a minute on this idea of vapor drive, because this really indicates one of the key things that's not necessarily well understood. So on the top we have a wall assembly in a warm, humid location. So we have warm, humid air on the outside. We're air conditioning. The water, the humid air, that vapor drive is towards the inside. And as the water migrates through the wall assembly, it comes to that blue dotted line, which is the condensation point. So the temperature inside that wall cavity, that insulated wall cavity, is continuing to drop as heat is transferred to that cooler internal zone, or vice versa. And at some point, there's a condensation within that insulation and or very close to proximity to the surface, like where the drywall would be. And that allows for moisture to wet up that material, and that then becomes a great host for the growth of bacteria, or black mold and other forms of bacterial growth. So this mechanism actually works just the opposite way in colder northern climates. So we have internally heated air that's warm and humid because of cooking and from just respiration. So moisture is generated on the interior of the building. The vapor drive is to the outside of the building where the air is colder and drier. And at some point, the same thing is happening where moisture is condensing somewhere in that thermal drop as we move through that insulation. And then that water can condense. In this case, it would be on the exterior sheathing of the building. So our general way to deal with this is to place a vapor barrier on the exterior of a building in a warm, humid climate and on the interior of a cold, dry climate. These are just two other illustrations, and this is hyperlinked in the slideshow if you wanted to go through it in depth. But it just shows the idea of moisture migration from hot to cold, and then vice versa here, and what's happening with the idea of where water is going to condense on what surfaces. Another good graphic of wind and its effect on a building. So this one shows you that you can have both a positive pressure and then create a negative pressure on the building. So there's a lot of changing and fluctuation in these pressures that can start to, through capillary action, drag moisture into the wall assemblies. So this is the most important kind of illustration of this this whole slideshow, I think. This is a typical way we build. So here we have a stucco system applied over a wall, or on the right, a conventional clad system. And we have building paper and or an air barrier and water barrier on the exterior of the building. And that allows for no drainage channel if water gets in, and no way for anything to dry out. And so we can start to talk about advancing that. We can texture the building paper, create a capillary break, allow water to be able to drain out of that assembly. But we also, once it's wetted up, we have no way to dry it. So the next step up in the kind of a wall assembly is to actually drain it and ventilate it. And we do that by creating a larger air gap where air can move up through that assembly. And here we have a good illustration of what's going on there. And then this is just a nice point they make. A Rainscreen is not a product. It's assembly applied to the exterior of the wall. It has performance characteristics to it. And I wanted to move on to showing you just the kind of growth in the thinking about what we're putting on the exterior of our buildings in order to build up these kind of moisture resistant kind of barrier system. So we start out with a typical building covered with Tyvek. They're just showing modes of failure. You can tear it, you can rip it, you cannot have it continuously applied. You can fail to tape the seams. All kinds of things can go wrong with it. So we're kind of advancing now in our thinking with exterior cladding, and you see a lot of this now in new construction, these weather-resistant boards, which have a weather-resistant barrier integrated or glued right to the sheathing board. And then the edges are taped in order to make that a continuous weather-resistant board. But it has problems, as I've shown you in some other detailing of it. Ends might not be capped. There may be breaks in the tape, damages to those surfaces also. But this is considered a step up from that idea of a continuous house wrap. And I think there could be some discussion about whether that is in fact true, but I'll leave that to other discussions. Then we get to the idea of texturing that up. So we have a drainable layer that helps to break that capillary action. And, they're showing you this by the house wrap is typically 1 to 1.5 millimeters thick. Surface tension of water is 1 to 2 millimeters. So we need to make that texture of that wrap to be 4.5 millimeters of airspace in order to do a capillary break. And then the next layer up is actually to I think we move from to this idea of an engineered drainage and ventilation mat. So these are the things that are going between the sheathing and the outside siding material that are actually creating both a capillary break, a water-resistant barrier in some cases, and a place for air to move through to dry out those assemblies. So they talk about that idea of creating space, a gap to ventilate, separation. And the last one here, I think I don't really mention much, but I think this is becoming more well understood, the idea of uncoupling the exterior siding material to the inside wall surface. So you can imagine sun shining on siding gets very hot. If it's touching the interior sheathing material, it can transfer that heat readily into the interior environment of the building. And in summers, when it's got a high, it can increase the cooling load on the building. But the idea when we create that air gap, we're uncoupling the exterior siding temperature and that thermal heat from the interior wall temperature. So there's a way that we're actually reducing heat demand or cooling demand on our buildings by that decoupling. A little bit on the standards. I wanted to get to one last graphic, but we have this idea of now of seeing our sheathing material, a large drainage mat that allows air to flow through it, and then our exterior siding system separated from that. And then there's obviously different types. So we go to these kind of non-woven, these kind of three-dimensional, as they call entangled net structures that are like just a mess of wire that can't be compacted down because they kind of glue to each other, and it just creates a kind of a springy surface of which the siding can be nailed to. And because it covers such a large surface area, once the panel is applied to it, that springiness is no longer there because it's spreading its weight out of so many over so many of these ridges within the assembly. Then we have these kind of mats. This could be an aluminum or some other kind of plastic material that just physically holds that siding off and allows air to move between it. And then kind of maybe a combination of using a typical Tyvek or house wrap, and then a furring strip. In this case, that furring strip is now this maybe plastic channel that just holds the siding away from the building and could possibly be nailed on the studs, and then the siding is nailed through that also onto the studs, and that just kind of maintains that kind of air gap. So the final thing that you should, I guess, really, talks about standards. Mostly how we're really not at the standards of requiring some of those kind of advanced Rainscreen assemblies yet, but I do think in the future they will become part of things that are commonly done and required by code. So last time, what is considered a Rainscreen? So we have a conventional sided building with paint closing up these gaps, not allowing this to be ventilated, the clapboard system. Now we have a more advanced clapboard system. Maybe the siding is pre-finished, so no paint is applied to seal up the gaps. There is a continuous drainage and ventilation channel behind it. All right, so that's that presentation. I have a couple of more things to say on our, there's in that site that you go to, there's some nice detailing about conventionally or creating these kind of Rainscreen wall systems. That might come up, especially if you're doing residential construction that you may not be familiar with. So I'd invite you to go to that site. Even the stucco systems now are talking about that idea of those kind of buildup of the surface to create ventilation channels and capillary breaks between the exterior stucco and the inside. And these are well documented in the manufacturer's kind of literature. And I didn't mean to go out to that. I meant to click to the next slide. One last thing. This is just some telling issues about where we're going with building performance. So this outside here, we have that on the very far right here. We have that siding system with the weather-resistant barrier. The green already applied. You can see each one of the seams is well taped. So we have probably a center tape and then 2 additional tapes alongside of it to create a really strong seal between those two. We have any openings marked and then taped over, and you can see where they're applying what looks like a power supply panel or a service entrance for electrical service entrance, how they've already got these pads set up to seal around where they're making those intrusions. And that's all going to where we are in building, with the idea of building tightness. So we have just two images. In case you're not familiar with this, I kind of cover this a little bit in environmental controls. But our exterior facade systems are then tested nowadays to make sure that they're actually, in fact, sealing as tight as they're specified to do. So they have these fans that they apply to the doors. They suck the air out of the building, and they do that in a continuous fashion. And then as air starts to leak in, you have a pressure differential between the inside and the outside. So if so these systems allow somebody to quickly calculate by excavating this air through the doors how much is entering through other areas, and that can determine what is the air tightness of the building and then the air change per hour. And so that is just part of what's happening in the advancement of analysis of performance. Now I've seen where actually on site, they may actually test specific areas of the panel for air tightness. So they might put a big ring of like an upside down bowl over a surface, apply pressure to it to find out how much air is leaking through a specified area in order to test these components prior to certifying them. So we'll pick up on the punch facade next.